Start. We have had a permutation in the title.
Oh, did I permute it? Oh, okay.
In my notes, it says equivariant trees and partition complexes.
Okay.
I think this is yeah, great as a footnote. Coming for the second topic, Julia Bergner from the University of Virginia.
And is commutative. So. And I'm going to talk about the partition complexes first. Yeah, so this is a project that this was joint work with Peter Bonventre, Maxine Caillé, David Chan, and Mario Sarazola. And just a quick plug, so this was part of a collaborative workshop in the Mid-Atlantic region, not the one that Dave was just joking about, in which case you'd be in the middle of an ocean, but the Mid-Atlantic states in the US. And there'll be another one of these this summer. I think a call just went out for application, so if you know anybody in that region, Anna Marie is one of the leaders of a team for it, so just a little plug for that. Anyway, so the idea here was we took some work that was done relating the notion of partition complex and tree. There's a couple different approaches in the literature of this, and we wanted to equivariantize it. So I guess that's maybe the theme, continuing from what Anna Marie was doing. We take something that's non-equivariant and see what happens when we do that. We make it equivariant. And so I think, I'm not gonna, where I'm going with this talk is not necessarily to talk about the deepest, most complicated results, but to sort of set up a story and then to talk about, there's a couple different ways to make it equivariant and kind of just to set up some notions that other people might find useful and then to kind of hint at what we might want to do with it. So, so the first part here for a while is I want to tell the non-equivariant story. And I'm mainly going to be following the way that this is done by Ika and Heiss-Hoytz. So, but there's another way to do it, which I will only have time to mention briefly, but this was due to Robinson, and it actually predates the Hoytz and Mordick one by quite a bit. But anyway, I can't tell both of the stories and actually get to the equivariant part. So, so let me just start. Perhaps partition complexes are familiar. They come up in a lot of, say, functor calculus talks. But let me do a quick review of that. So let's let n just be set with n elements up to n, and then we can partition this. So the partitions of n form a poset, and well, you have a choice which direction you want the poset structure to go. I'm going to choose that this is under coarsening rather than refinement, which is the opposite, by the way, of what Hoytz and Mordick do. So if you bigger, coarsening means you take unions. Yeah. So I'll draw a picture here to clarify this. So just as an example, when n equals 3, so there are 5 possibilities here. So you have the indiscrete partition where everything is all together. You have the discrete partition where everything is separate. And then you have the ones that sit in the middle with 2 elements in one and 1 element in the other. And so I'm going to draw these. I mean, it's a poset. I'm often actually thinking of it as a category, so I'll draw arrows instead. So, so our coarsening goes from, something with more sets in the partition to something that has fewer sets in the partition. Okay, so now if you were to take these posets and you want to geometrically realize them, then you're always going to get something boring because you always have the discrete partition and the indiscrete partition. Having even one of those would guarantee that the geometric realization is contractible. So you always have an initial and a terminal object. So we want to fix that. Yeah. Okay, so we make the following definition then. So for any n, at least one, then we define the partition complex so Pn to be the poset, and again, I'm generally secretly thinking of this, or not so secretly thinking of just the category. Actually, no. I'm going to move to simplicial sets right away. So I want this to be the nerve of the poset of non-trivial partitions of n. The reason I had to check which convention I wanted, you'll see this notation and other different notations, but sometimes they mean the poset, sometimes they mean the nerve, sometimes they mean the geometric realization. So you kind of always have to check what your reference is using as a convention. Okay, so some small, very small examples. Well, first of all, if you take P of 1, that's going to be empty because there are no non-trivial partitions. Likewise for P of 2. So P of 3 is the first interesting case. And well, once you get rid of these top and bottom ones, you don't have very much interesting structure left. But this gets complicated quickly because already P4 just gets very complicated to draw. So if you would like to attempt to do that, I'm not going to. But the structure here is not random. And in fact, if you take the geometric realization of Pn, this is homotopy equivalent to a wedge of spheres of dimension n minus 3. And in fact, there are, I think, n minus 1 factorial of them. You can check that checks out. For p equals 3, it's a wedge of 2 copies of S0. Okay. And so these are, as you can see, this is not too difficult to define. I mean, this is actually tracking down a proof of this in the literature is quite difficult. It's easier to actually find a proof for trees once we've done the comparison with trees. But anyway, we have this nice description. But these have a lot of applications. And this is the homotopy theory audience, so maybe people have heard about this in functor calculus. So they're used to give a description of the derivatives of the identity functor. They also have some applications to Lie algebras. This is very combinatorial. A lot of combinatorics people have studied this as well. So there's a lot of things that you can do with it. You might find it's interesting. But what I want to focus on today is a relationship with trees. So and so slightly more precisely, but not completely precisely yet, we're going to have a functor from the simplex category of Pn to some poset of trees. So this is just this general, very general construction. So you've got a category, objects are the simplices of Pn, and then this is going to be some poset of n trees. And I'm going to defer the definition of that for just a moment because I think it's helpful at this stage to just give an example of what this correspondence is going to look like. So I'm going to let n be 6 here. And here's an example of a 2-simplex in P6. So this is a two-stage coarsening. And so I want to associate to it a tree. Now, I'm not going to give a formal definition here of a tree, but if you can sort of extrapolate from the examples. If you're familiar with operatic trees, that's what we're using here. So typically we have leaves at the top that don't have vertices at the top. So we're going to start. So we're going to have 6 leaves labeled. And then we're going to start joining them up based on what's indicated by the partition. So here's our most refined one. Everything is separate except for 3 and 4. So let me join up 3 and 4 here. Everything else is just going to have a vertex like so. And now I have this coarsening, and now 1 and 2 are going to join up. 3 and 4 just stay by themselves, and 5 and 6 are going to join up like so. And then we're going to have these two join together, and then this will be left alone. And then we always just, by convention, just kind of stick them all together so that we get an actual tree. And we're going to divide this up into layers. Maybe I'll use some color here. Okay, so we consider this is 0, 1, and 2. Okay, so the idea is, so up here, we have things sort of joined up as indicated by the first partition, second partition, and then the third partition. This is the 2 simplex, and then this is just kind of canonically always there. It's not suggestive of any further coarsening. Yes, yes, I'll give a definition momentarily of that, yeah. But yeah, the n is going to mean how many leaves it has. All right, and then, well, you could say, well, then what happens, say, when you take a face map? So you look at one of the faces of this 2 simplex, what happens to the tree? So applying face maps, the DI is going to contract the edges at layer I. So So if I apply D0 to the tree that I have up there, then I'm still gonna have my 6 leaves, but now I'm gonna join some of them up faster than I did before. And then we just shift the indices. So this now becomes 0, and this becomes 1. And this corresponds to, well, I don't want to write it out again, sort of the second coarsening above, which is a 1 simplex. All right. So now let me give you some definite. So now hopefully you have maybe some idea how you would do this. Now let me give you some more formal definitions of the kinds of trees that we want. Okay, so an n-labeled tree, or sometimes we just call this, I mean, sometimes I underline it, sometimes. Or n tree is a tree with a labeling bijection from n to L of t, the set of leaves. Let me call this t. Okay. So implicitly, there are n leaves here. Now, we had some extra structure on here in that we sort of had the leaves all together sort of in a row. We sort of had the same distance from every leaf down to the root, even if that meant having some vertices in the middle that weren't doing anything interesting. And so that's what we call layered. So if there is a constant number of inner edges between any leaf and the root. So you can see that in the examples. On the other hand, you may want to get rid of these unary vertices where you just sort of have one incoming, one outgoing that aren't. I mean, in our situation coming from the partition complex is where the partition sort of doesn't change. That set in the partition didn't move. So we say it is reduced if there are no okay. So those are our tree definitions. And now I can tell you what this script Tn is. So we're going to define Tn to be the poset of isomorphism classes. And actually, I think probably to be compatible with Pn, I probably want this to be actually the nerve of the poset of isomorphism classes of reduced n trees. But then I need to tell you what the maps are. So with t to t prime, a map here when t prime is obtained from t by contracting inner edges. Now, if you work with these kind of trees a lot, you might protest. If you remember at the beginning, I said we had the opposite poset structure as Hoyts and Moerdijk did. You do refinement rather than coarsening, and that's going to affect the direction that we want. So in particular, if you're familiar with the category omega of trees, this is the opposite direction from ones in the category I've just described is not the opposite of omega, but if you're used to the way the maps go in there, they go the opposite direction. So just a little warning there. Okay, and then the last thing I should comment on here is that, again, if you take the poset of all of these, we want to omit, there's a terminal object here, which is the end corolla. So we throw that out so that this nerve will not be contractible.
Reduced animal trees, but they're not assumed to be layered.
Exactly. So yes, you're anticipating what I'm going to say next. So the idea, no, it's good. People are following where I want to go. So the idea is we want to do this construction that I've described here, but we want to add an extra step. So we naturally associate to a simplex a layered tree, but then we reduce it. And then that gives us, so it's a composite of those two things. So a bit loosely speaking, so we define this. Again, there's an induced map of posets or categories. There's a map of posets or categories that induces a map on their nerves. So by associating a layered tree to a simplex, and then reducing. So this is the process described above. I'm not going to spell it all precisely, but that's the idea. And then the nice thing you can check here is that this functor is homotopy final. And so that tells us then, so by equivalence theorem A, that it must have an induce a homotopy equivalence on geometric realization. Okay, and then, but then there's also equivalence theorem A argument. You get a homotopy equivalence from the simplex category to the original, the geometric realization or the original PN. So that's how that goes. Okay. So then the last thing I'll say, I mentioned there's another way to do this. There's another story I could have told here. There is also another proof that instead of going through the simplex category, you go through some space of trees. And these are something called, well, we call them measured trees. I think there's a couple different names for them, but which is called TN. And so this is the approach that Robinson uses, and I think Sarah, you were on a paper that dealt with these, right? So you can also ask Sarah about these. Okay, so that's the end of the non-equivariant story. Are there any questions at this point? All right, so now I want to tell the equivariant story. And something we ran into right away was, well, what is an equivariant partition? And it turns out, well, there's a couple ways, multiple ways that you could possibly think of as being a definition. So the first thing is a little bit of a change of perspective on partitions. I mean, I've kind of just been manually drawing them out and dividing things into subsets. But we can also think of a partition as a surjective function from n to some smaller set k. And technically here, I think you want to mod out by the sigma k action. So if we do that, then there are a few generalizations. That you could imagine for a G set A. And I'm just going to assume that G is a finite group. Well, the first thing you could do is just say, well, you can kind of just ignore the G action and just partition it. So that would be the first thing. So you could say, well, just partition A into subsets. This is a non-equivariant map. And these form a poset. And I'm going to call this P of A. At the other extreme, you could say, well, let me take another G set, B, and take equivariant maps between these two G sets A and B. And this gives you something that we write as P upper G of A. Now, there's something in the middle that you could imagine doing, whereas you also take another G set, B, but you take the non-equivariant maps between them. So it's kind of a hybrid of these other two things. And informally, among my collaborators, we call these the weird partitions. We can't really figure out what they mean, and I think when I talk about the transition to trees, you'll see that it's hard to imagine what that would translate to. So what I want to do next is just talk a little bit about what these things are, what they look like, and then talk about their corresponding kinds of trees. So let me start with this sort of less equivariant version. So we're going to let P of A be, again, the nerve of the poset with objects, so equivalence classes of maps, surjective maps from A to K modulo the sigma K action, and then so the morphisms, again, should just be some kind of coarsening. So, so you have a partition from A to K, and then you have another partition from A to J, and if J is less than or equal to K, then you've got a morphism there, making the diagram commute. And then, so as before, we're going to throw out the uninteresting one. So in our new framework, that looks like A going to the set with the same number of elements as A, and then the map from A to 1. And you might say, well, okay, this is kind of weird, though. Why do we? It doesn't seem like we care that A is a G set at all, except that this poset has a G action. So if I have a map from A to K, then I can just precompose by the map given by G inverse, and that'll give me a different partition. All right, and now we can do the same kinds of things with, we can move to some kind of tree from a simplex in here. So we can associate a simplex in P of A to a tree, and this will have an action of G just on its leaves. So here's an example. This is an example that appears in our paper. So let's let G be C4, and I'm going to denote the elements here by 1, I, -1, and -I. And then I'm going to take A, will be a set with 6 elements. So I'm going to have X, which is going to be identified with -X. I'll have IX, which I'm going to identify with -IX. And then I'll just have Y minus Y, IY, and minus IY. You can also think of this as C4 disjoint union with C4 mod C2. I just want to have names for everything so I can label them on the tree. So now I'm going to consider a 1 simplex in P of A. So I'm going to have XY, IX, IY, and minus Y minus IY, and I'm going to just merge these second 2 sets here. Okay, so observe that, these partitions are not what you might think of as being G equivariant. They're not preserving things being in the same subset or anything like that. So this is sort of not C4 equivariant. But here's the associated layered tree. Draw the layers in. Okay, and so you could say, all right, now if I look at these, they're a little bit in the shadow, I'll put it up momentarily. These labels, they correspond to elements of A, but just as you can see, okay, this partitioning isn't respecting the G action, you can see that this G action isn't on the whole tree. If you tried to see what was happening when you go further down than the leaves, things just aren't going to be preserved in the way that you might want them to. So the C4 action is just on the leaves. Not on the tree. All right, so that's how, it's basically the same construction, you just happen to have this action on the labels. But now let's look at the version further to the right, the more equivariant version, where you're going to partition a G set into G sets. Into subsets that then have a G action on the collection of the subsets. So let's let P upper G of A be the nerve of the poset of equivalence classes. So now these are going to be G surjections from A to some other G set B, modulo the automorphism, the G morphisms on B, and then for morphisms, if we have some B and some B prime, you would just want, but you'd want everything in sight here to be equivariant. And again, we exclude the uninteresting things, so exclude any maps A to B that are actually isomorphisms, and then any map from A to still just write it by one, just a one element G set. But notice that somehow the fact that we've required the maps to be equivariant means that the poset, or the nerve of it, does not have a natural G action. We sort of used it up in making the maps be equivariant. And in fact, we actually have a relationship between these two structures. So if you have P of A, which does have a G action, if you take the fixed points by a subgroup H, then this will be equivalent to PH of A. So for H, a subgroup of G. And in our paper, we decorate this, but this is just A as an H set. So we have this kind of nice relationship between these two different versions. So you can start to see where, okay, these play nicely with each other. How do you fit in the thing in the middle? We don't know. But now let's look at associating a tree to this, to a simplex in this P upper G of A. So let me keep reading things for just a minute. So again, let me do the same thing. G is equal to C4 and A as above. So my set and my group are the same as in the previous example, but now I'm going to look at the one simplex where now I have X and IX, Y and minus Y, IY minus IY, and then again, I'll just merge the second.
When you say in fact, on the left-hand side, do you mean the weird one or the left-hand one?
This is the left-hand one. Yeah, I didn't give a name. I'm not using the weird one. The weird one is not appearing.
But you're letting H act by just on A. So
Right, so I mean, I said that PA has a G action. So it would have an action by any subgroup of G, so take the fixed points. That's all the left-hand side is.
that seems like it corresponds to being H equivariant with respect to the trivial action on K bar. Whereas in the other example, you seem to allow non-trivial actions on B.
No, I mean, all I should be using here is just the G action on that I've described here, which is completely just using an action on A. There's no action on K. Right. I mean, maybe you implicitly want a trivial action, but
non-fixed to non-trivial.
Yeah. Oh, yeah. Yeah. Right. Okay, that might be where the issue is, that the quotienting out by the automorphisms of B. Maybe we can talk about it. Yeah. Okay. Okay, so now, so the corresponding tree here corresponding layered tree wrong one. There we go. Okay. So this is the layered tree. I'll draw in the layers again. Now, this is where we actually want to do the reduction. So if we reduce this tree, so we contract this edge here. This will not be layered anymore. So let me remind you that x is minus x and ix is minus ix. Okay, so it turns out now that we actually have an action of G on the whole tree after reduction. So if I'm going to label the edges here so you can see what's happening. So if this is A, then this would be IA, and A is going to be the same thing as minus A. IA is going to be the same as minus IA. If I call this C, this edge should be minus C. Similarly, this should be IC, and this should be minus IC. That's what's going to make this, what's going on with the Y's and the IY's compatible. If I call this D, this should be the same as minus D. This needs to be ID, which should be negative ID. And then these are all going to be fixed. So I can call this BE, and then I'll call that one R for the root. Okay, but the point is that we have a C4 action on the whole tree, not just on the leaf. So it's more compatible with the rest of what's going on, at least after we reduce it. It doesn't work quite on the layered version. Okay, and then we'll define T, G. Actually, I don't know that I defined, I'm not sure I ever defined what TG was. Sorry, just T of A, but okay. So this is the poset of such trees. And so just a remark about these, that these are closely related to the G trees of Bonventre and Pereira, if you've seen those. So they define what they call G trees, which are the orbits of our trees with G action.
You were saying that it's important to reduce them. I'm going to have a G action if I don't reduce it. Or you say that the G action is not going to preserve layers or something?
Well, I mean, at the end, because the comparison, I mean, this is where we really, I guess this is where we want the G action, because this is the category of these things is the thing that's going to end up being equivalent to the. Yeah. Actually, I mean, it's not. It may still work on the layered one. It's just this is where we're trying to go if we're trying to tell the same story. Yeah. Yeah. And well, I mean, so Peter and Luis got a ton of mileage out of this. They did this whole theory of, equivariant operads with norm maps, and did a lot of nice things there. And we would definitely like to tap into that as well. Okay, so let me state our main theorem. So the functor from the simplex category of P of A to T of A. I'm not 100% sure I defined this, but this is the analog to P of A, the tree category. So this is G homotopy final. which is a notion actually in the appendix of our paper. We give a proof of a G-equivariant quill in theorem A, that from which we get what we want from this. And then the other functor from on the G versions. So this is not, these don't have a natural G action, so this is just homotopy final. So we get equivalences on these geometric realizations, just like we had in the non-equivariant case, which is what we wanted. And again, that's composing with the thing from the category to the simplex category. But let me go back to this this myth that it's now erased, but this one that we called weird. I mean, you can say, all right, well, you have something where you just have an action of G on the leaves. You have something where you have an action on the whole tree. But then if you sort of have this, it's not clear what these sort of non-equivariant maps between G sets would correspond to here. And that's why we kind of abandoned doing much with those. We couldn't figure out how to put it into the picture very sensibly. And then we also, I mean, I mentioned there was also this other way to prove it. So there are also these spaces of measured trees. So we have a T of A and a T G of A, and you know, in comparison using those. So you can tell the whole story in that from that approach as well. Again, that's just a different talk I could have given. So, so I just have a few minutes left. Maybe I'll just say a little bit of what we did with this. So we did look at so if you have this space here, we had the non-equivariant case, we had this really nice description. It's this wedge of spheres, and so we said, well, can we say anything about this? And what's its G homotopy type? It ends up being pretty complicated. There's also some related results about this by Aron and Bergner. But we sort of said, with some fairly serious hypotheses, we got some results about what the homotopy type is. For example, if G is solvable, H is a normal subgroup, and A is H isovariant, then you can write this space here as a wedge of spheres of the same dimension. And I mean, we're describing this to, get at this because this is the thing, because of this fixed point relationship between them. So it's much harder to really get some kind of nice description of these spaces. It's just much more complicated, which is maybe to be expected. We also looked at some connection with Lie algebras. I mean, this is what Alan Robinson did in his paper, was kind of do this comparison, with these little Lie algebra pieces, the things that end up making up the Lie operad, and we were able to get an equivariant version of that. Again, that's just a whole nother story I don't have time to go into. And our group is kind of still thinking about these things. Unfortunately, Peter Bonventre has left math and is not working with us anymore, but we recruited Angelica Osorno to be in our group. And so we'd really like to make this connection with G operads. How can we really understand how we could fit this in to the Bonventre and Pereira work? I mean, we also just, a lot of these kind of ideas come into like Michael Ching's thesis. How much of that you've got to like bar construction, you've got this construction of operads, connection with functor calculus. How much of that can we do in the equivariant case? There is the question of equivariant functor calculus, which I understand very little of. Anybody I know who's thought about it says it's ridiculously complicated. So that's maybe a longer term goal to try to understand what that is. But it seems like there are lots of things this could be useful for. And so I hope it will. And anyway, so I will stop there.
Sorry, did you say, so the second one with the fixed points,
Mm-hmm.
is that deduced from the first thing by just take? Can you deduce that from the first version by taking G?
Can you deduce, oh, can you deduce
Yeah.
this one from this one? Possibly. Yeah, yes, because I think we actually showed that this is actually a G equivalence, which would mean that you have equivalences on fixed points. So yeah. I don't think that's what we did in the paper. I think but yeah.
Relatedly, you didn't talk about TUA as a G action. It does have one.
Yeah. Yes. Yeah. Just for the same, basically by the same. I think somehow I neglected my definition of TAA and to mention that it has a very analogously to the G action here. There's a G action here. So, so yes, this is. Yeah, and then you have the same. I mean, even before you get to this, you have the same relationship between the TA and the TG of A.
So you said under some very restricted hypotheses,
Yeah.
Do you have an example where you know it isn't a wedge of spheres?
I think, I mean, I can't, I think so, yes. I think, don't ask me to give you a concrete definition off the top of my head, but if you look in this section of our paper, wow, it's a miracle that this is ever a wedge of spheres, something that's that uncomplicated.
Actually, could you say some more about that? When you do know it's a wedge of spheres,
Uh-huh.
are you saying it's a wedge of G mod H plus smash of sphere, or is it a representation sphere? Or do you know the action on the sphere?
I don't know the answer to that. I haven't thought about the intricacies of that. I'm not. I would have to go look it up. I don't. Yeah, I don't want to say anything.
Where I originally thought you were going was to get the symmetric group to act on that wedge of spheres and look at the action on the homology. Presumably, if you have sign coefficients, you get the Lie module or something like that.
Yeah. Yeah, I think that's this like Lie algebra, or I'm calling it the Lie. It's not actually Lie algebra. Yeah, it's this. Yes.
The cross terms in the algebra.
Yes.
Yeah.
Yes. I always forget the concise way to say it. Yeah, yeah.
All right, well, thank you again.